everyone. Let's settle down. All right. So, I guess before we begin, any questions about the homework or uh, or any of the setup for the review sessions and all that? Go ahead.
I just have a question, but if you're going to cover it,
Well, I guess let me go through the topic, and then if you have a question. I'm not, for the homework, yeah, you don't need any of these integral theorems that I'm going to talk about today.
So it's about the n vector for the integral of your tensor.
Okay, yeah, I'll talk about it then. Yeah. Anything else? All right. So, very quickly, what we've been talking about is calculus of scalars, vectors, and tensors. So we went through derivatives of scalars, derivatives of vectors, and last time we introduced this divergence of a tensor field. And I pointed out again that the definition of that divergence is very similar to all of the other derivatives that we've created. Flux of the tensor field, which is measured by T acting on N on some surface. So for example, if I go back to one of my velocity fields down here. So let's say I have some cube type body, which is given here. And instead of this velocity field, I have a tensor field. And I pointed out last time that a tensor field would associate with each point in the body some tensor, like some ellipsoid. So instead of these arrows, tries to visualize a tensor field which would be a bunch of ellipsoids all over the space, right? So that's what a tensor field is. Now, when we are talking about divergence of a tensor field at some point x, what we are again saying is that go to that point x, surround yourself with some small infinitesimal body, and on the surface, on the complete surface of that body, you have these surface normals, n. And what we'll do is take the tensor field, tensor at that point, act it upon that normal, that will give me yet another vector, right? When tensor acts on a vector, it gives me another vector. So we'll do that for this entire surface, and we'll take the surface integral of that quantity. First question, tensor acting on this normal will produce what type of quantity? A vector. A vector integrated over the entire surface of that small infinitesimal body will give me another vector. Yep. So T acting on n will give me a vector. Take that vector, integrate it over the surface of the body. And by the way, what do I mean by integrate a vector? What happens when we integrate a vector? When we integrate scalars, what happens? We have some function and we are adding up the function value times dx, right? F dx is what we are adding up. In the same way, we are adding vectors now. If you think of that vector times dA, that's a small infinitesimal vector. Then we know how to do vector addition. If I have one vector times dA, I have another vector times dA, I can add those two. And if I do that infinitely many times over the entire surface, that's what that surface integral would be. So that will produce some vector, divide that vector by the scalar volume of that body, and that's what the divergence is, how the divergence of a tensor field is defined. In components, it's much more straightforward. Just take the tensor partial xi ei. So partial xi ei, that was the derivative operator that we had defined up here, somewhere, I guess, on the previous page. This was the partial operator that we had defined, the delta operator. And what we said was doing this is actually the same as taking the tensor and acting it on that partial operator. So you can calculate it with any of these expressions, a divergence of a tensor field. We did this example. We came up with divergence of this tensor field, which we sort of tried to visualize last time, came out to be a vector field of minus 6x. Okay, so that was just the definition of or how you can take divergence of a tensor field. Let's see how we can work with some of these derivatives, because when we have fields, we can take derivatives. We also have to integrate it back sometimes, which is going back uh, to the fundamental operations on fields that I had told you about. In 1D, if you have a function, you can take the derivative. We all know how to do that. And the reverse process is integration. If I have the derivative of some field f, if I integrate it between a and b, assuming that derivative is continuous, then what I get is that the value of that integral is equal to the function value at its boundaries themselves. Okay, so let me make sure we understand this. We have some one-dimensional domain A to B, right? That's a line segment. Now, what we are saying is that over that domain, I have some field function, scalar field f defined up there. If I take the derivative of that field, I get this df dx. I can also plot that over that same domain. If I try to integrate it back, I should get back the original function fb minus fa. That is, I've converted an the integral over the body itself, the body being AB, to something that is evaluated over its boundary. Okay, so f boundary of this body AB is nothing but 2 points. It's a one-dimensional line, so the boundary of that one-dimensional line would be just 2 points A and B. And this idea of converting the derivative over the region of a body to something that is over the surface of the body is what all of these integral theorems that we're going to look at are focused at. So we've done derivatives for scalars, vectors, and tensors. We are going to do some integral theorems now to try to convert them back to be able to integrate them back to fields. So one of the most basic theorem that we will use a lot is called the divergence theorem, sometimes also called the Gauss theorem. And for vector fields, what it says is that take any body V. If you have some vector field Vx defined in over the space, then calculate the divergence of that vector field and integrate that over the volume of a body. So here, let me go back to that. Let's go back to this vector field. Okay, this is a vector field defined over the entire space. When I was defining divergence, I chose a small infinitesimal body. But now I'm not talking about some small infinitesimal body. I'm saying that pick any sizable body you want in here. Any finite size body that you want in here. And what we'll do is we'll calculate the divergence of this vector field. What type of quantity would a divergence of a vector field give me? A scalar field, right? So if I have a vector field, the divergence of that vector field would give me a scalar field. I'm saying that take that scalar field, which would be some sort of a color, right? And integrate that scalar field over this entire volume of the body. Okay, so there is some volume of this body B. And that integral is going to be equal to V dot N over the entire surface of the body. So that's what the divergence theorem says, that if I have some vector field, take the divergence of that, that's the derivative of some vector field, integrate it over the volume of the body, that will be equal to the same vector field dot product with a unit vector that is normal to the body and integrated over the surface area. So I hope that this equation or this theorem looks analogous to you with what we had talked about for one dimension. Integral of the derivative of some function over the domain of that body AB is equal to the function value or flux. Actually, this is really just the flux at the boundary of those at the boundary of that body, which in this case is just 2 points. So that's this fundamental theorem of calculus that works for scalars is what we are talking about here for a vector field in 2D or in 3D. Derivative of some vector field over the volume of a body is equal to the flux of that same field over the boundary of that body. It just so happens that since we are talking about in 2D and 3D, that a boundary of a 3D object would be a 2D surface, right? The boundary of a 2D surface or a 2D area would be a line or a curve integral, right? The boundary of a line segment would be just 2 points, which is what we saw in the fundamental theorem of calculus. So, and I think what we'll do is take an example, a very simple example, and see whether this works at all. By the way, this does not place any restrictions on what type of vector field is it. It should be continuous, and it does not place any restrictions on what type of body it should be. It could be any body, right? So for example, in your homework problem, you had a cylindrical body. Just as well, you could have taken a sphere or a cube or a tetrahedron or whatever. Any body you choose, this quantity, divergence of the vector field integrated over the body, will always be equal to V dot with n over the surface of the body. Okay, so the vector field itself does not have anything to do with the body, the cylinder itself. But let's take an example of this vector field that we've now become very familiar with, the vector field X, growing arrows outside from the origin, right? If I try to visualize that in 3D, and if I choose the body B as a sphere of radius R here as I've drawn, then what we want to do is to verify that this divergence theorem works. So you remember what we calculated for the divergence of this vector field, V equal to X. What is the divergence of this vector field Vx that is equal to X? Yep, we did calculate that. So V is Vi EI. Divergence of V is partial xj of Vi EI dot with EJ. We know that this guy is delta IJ, and so that gives me Vi comma J E, sorry, there's nothing here, Vi comma J delta IJ, and if I contract out J, then I get Vi comma I, right? All I need to do is to take the partial derivative of V, the components of V, with Xi. So if Vi is Xi, then that implies that divergence of V of X would be just Xi comma I, which is nothing but delta II, which is nothing but 3. So we've done this, I think maybe in a previous lecture. So we'll write that here, that divergence of that quantity of that vector field is a constant scalar field 3. It associates the scalar 3 with each and every point in the space. So the left side integral of this divergence theorem, left hand side of that integral turns out to be integral over the volume of 3 dV. You agree? I am calculating this integral over the volume of the constant scalar 3. 3 is constant, of course, I can pull it out. Integral dV is what I'm left with. What is integral dV for a sphere? right? The volume of the sphere, which is equal to 4 over 3 pi r cube, and putting that factor 3 up ahead, cancel that off. I get 4 pi r cube is the result of the left hand side of that divergence theorem. Let's work on the right hand side. The right hand side requires this v dot n. Okay, this n, as I said, is a unit normal to the boundary of this body that I've chosen. In this case, or in any case, in any body, the normal will change from point to point, right? It's not a constant vector. For a sphere, is there a good way to figure out what the direction or unit vector normal would be, outward normal? Yes, it is in the radial direction. So if you attach the origin here, if the origin is attached at the center of the sphere, then the position vector of this point on the surface is x, right? I know for a fact that the unit vector should be along this radial direction. So can I say that n is equal to x? Right, x is not a unit vector, but it's pointing in the right direction, but it's not a unit vector yet. So all I need to do is to divide it by its magnitude, and now it becomes a unit vector pointing in the radial outward direction, which would be the correct direction for the unit normal. And in the same way, for your homework problems as well, you have to use some logic to try to figure out how to define a unit normal as you go to different points on the surface. Is that something related to your question, Joe? So, um, okay, let's now try to figure out the right hand side of this integral. We had RHS, which is area over the surface. So for now I'll just write it as integral over the area of v dot n. V is just x, dot with n, which is just x over its own magnitude, and that's v dot n, and I would want to integrate that over, excuse me, the surface area of the entire body. Can we simplify this? X dot x, what is that? That's right. So it's magnitude square, and we are dividing it by the magnitude. So the result of all of that is nothing but x, the magnitude of x. I want to integrate the magnitude of x all over the surface of this body. Now, if I go to any point on the surface of that body, what is the magnitude of x equal to? It's the length of that vector, right? It's from the center pointing to some point on the surface of that sphere. No matter which point I pick on the sphere, the magnitude of that vector will always be the same. It will be equal to the radius of the sphere. The direction obviously changes, but we are not really integrating the direction here. We're just integrating the magnitude, which again is just capital R, a constant. So I can pull that out of the integral. I get R integral dA. What is integral dA for a sphere? The area of the sphere, which is just 4 pi r square times another r, we get 4 pi r cube. And clearly left hand side is equal to right hand side. So that verifies the this divergence theorem for a simple vector field x over the sphere. And of course, as I mentioned, this is a very general theorem. As long as your vector field is well behaved, meaning continuous, not sudden jumps and all that, then you can verify that this theorem will always work for any type of body. It doesn't have to be a sphere, doesn't have to be a cylinder, a cube, or whatever. Some random shaped amoeba, it would still work. Okay. All right. So related to that, there are some other integral theorems also that are very useful. We looked at the divergence theorem for a vector field. There is an integral theorem for the gradient of a scalar field. Gradient of a scalar field gives me a what? Gradient of a scalar, a vector field. right? So gradient of a scalar field, let's say scalar field G, that would give me a vector field. Integrated over the volume of a body, that would again give me a vector, right? Not a vector field. Integral over, um, so G is a scalar field. Gradient of G is a vector field. If I take that vector field and integrate it over a body, I get a vector, not a vector field over the entire body or anything, right? So I get one vector here on the left hand side that has the very same form. Take that same function, flux over the boundary of that body, G times N. So this is just a scalar multiplication of a vector. Again, integrate that over the entire surface area of that body. We again get one vector. Left hand side, right hand side, both are vectors in this case. Gradient of a vector field. What does gradient of a vector field give me? A tensor field, right? So if I have a gradient of a vector field, that would be a tensor. Sorry, a tensor field. If I take that tensor at each point and multiply that with dv, integrate it over the volume of a body, what do I get? A single tensor, right? I get a single tensor on the left hand side. V dyad with n also gives me a tensor. Integrate that over the area, also a tensor. So, but in all these cases, you see the same form. Derivative of some field, and on the right hand and integral over the volume of a body, and on the right hand side we have the same field acting in some way or combining in some way on the normal or unit normal vector on that body and integrated over the boundary of that body. So same thing for a tensor field. Divergence of a tensor gives me a vector field. Integrated over the volume gives me a single vector. And on the right hand side, I have a tensor acting on the normal vector. That gives me a vector field. Integrated over the area of the body, that's a single vector. It is this function, the divergence theorem for a tensor field, that you have in your homework problem 3. Right? You don't have to use this. The homework problem asks you to calculate the left hand side in one case and then the right hand side in another case, and of course you should get the same answer in both cases. Okay. Um, so there are other integral theorems that I will actually skip. Uh, we are not going to be making use of these curl theorem or the Green's theorem too much, but I've given you a link and um, um, some more information about these things, which you can look it up if you ever need to use it. Okay. All right. So let's see. Can we? Are there any questions about any of these integral theorems? What overall we did was we set up a lot of different types of derivatives for scalars, vectors, and tensors. And we looked at these integral theorems. That derivative of those field over the volume gives me that same field acting on the normal over the boundary of that. So once you do that homework problem 3, I think these things will be more clear. By the way, how many of you have been able to solve that homework problem 3 by now? Not yet? Not too many? Okay. All right, so we'll talk about that more maybe today in the review session if you're having trouble. But I guess I'll stop with calculus of vectors, tensors, and scalars here. And what we'll do is switch gears and start with some real mechanics. Okay, so we spent almost a quarter of the course doing mathematical preliminaries, trying to understand the language of mechanics, and now let's get into some mechanics. All right, so the first topic that we look at for mechanics is basically how to describe deformation of objects, deformation of structures. So what we are saying is, if I have a solid body or if I have a structure, when we apply loads or when we apply some boundary conditions that cause the body to deform, all we want to do for now is to just describe that deformation mathematically. We know that uh, if you apply more load, you will get more deformation. So we are not trying to correlate the applied load or the stress that's built up in the body because of those loads. We're not trying to correlate that with deformation just yet. We'll come to that in chapters 3 and 4. But for now, all we want to do is to describe how the body deforms. Okay, and that's what this study of kinematics is called is all about. So, quick word here about deformations. We've already seen that all deformations are dynamic. There's no such thing as a static body, right? Each and every body, even though it looks stationary or static, there are some small ambient vibrations already going on in that case. But we, for our purpose, will neglect all of that. I'm sure those of you who are taking dynamics are seeing that, right? Things keep vibrating in dynamics, but we are not going to look into that. For now, we are just going to look at things that are static. So um, what that means is that either you can think about the deformation of a body at a particular instant of time. So if I have my body, initial undeformed body like this, it might be oscillating, but at a particular instant of time, I've captured like this photograph of this body, and I'm going to try to describe mathematically what this particular deformed shape looks like. So either we can think about this topic of kinematics that way, or you can think about a steady state. What is steady state? After all the vibrations, after all the big, large-scale vibrations are died out, the the body is sitting almost like looks like at rest. All these things around us, they are in steady state. Okay, there are some small vibrations underneath, but there are no large-scale vibrations overall. So it's kind of in a steady state. And what we're describing now is some sort of a steady state for each object. So with that in mind, let's see some basic definitions of deformation. Um, I'll introduce this concept of the stretch of a material in 1D, and then I'll come to your familiar definition of strain. But let's first define stretch. What we are saying is that if I have this body initially undeformed of length L0, shown here in black, um, then after some process happens to it, maybe I apply loads, maybe I apply boundary conditions, maybe I heat it, maybe I do something to it, the length of that body changes from L0 to L, shown in blue. So what we are going to do is to say that we define a quantity stretch lambda, which will be equal to the final length divided by the original length. Final length divided by original length. That's what stretch is. Okay, and I'm going to write the same equation or the same definition in a slightly different way, but a very important with a very important interpretation of that. We are saying that the final length of a body uh, can be obtained by taking the stretch of that body and multiplying it with its initial length. Okay. So it kind of sounds like I didn't do anything here. I just took L to the other side, and I'm saying final length is lambda times L0. This form of interpretation of stretch is going to be very helpful to us for 2D, 3D problems in general when we are looking at strains in for sort of not just bodies that look like lines, but bodies that have finite dimensions in 2D and 3D. All right, so using this definition of stretch, we can go through a number of definitions of strain. What is strain, by the way? When I say strain, what do I mean? Or what do you mean when you use the word strain? Measure of deformation. Yes, indeed, it is a measure of deformation. So if strain is 0, then we are saying that the body has not deformed, right? It could have still translated or have done a rigid body rotation, but there is no deformation, indeed. Is there a unique definition of strain? I mean, we've all used this strain is equal to small change in length over original length, right? That's what our undergraduate definition of strain is. But as I'll show you, that's a very approximate definition that holds under very specific circumstances. So let's take a look at that definition. Engineering strain, which we say delta L, change in length of this body divided by the original length. I can write delta L as final length minus initial length, and I come up with something like lambda minus 1, right? This first one is here lambda, and minus L0 over L0, that's 1. In fact, I can set up a number of definitions up here where if the final length is the same as the initial length, then stretch is equal to what? If the final length is the same as the initial length, then the stretch is 1. And if I subtract lambda minus 1, I get 0, right? So final length is equal to initial length, there's no strain. Makes sense? If I choose a different definition, something called a natural or a true strain, where we say delta L divided by final length, okay? Now in that case, I have 1 minus 1 over lambda. If final length is same as the initial length, I again get 1 minus 1 over 1, that's 0. In fact, you can pick any function you want as long as it, any odd function I should say, odd function hopefully you all know is basically something that, something that goes to 0 when lambda is 1 and is less than 0 when lambda is less than 1, because strain would be negative, compressive strain, and is greater than 0 when lambda is greater than 1. So any monotonic function that goes to 0 at lambda equal to 1 is a valid measure of strain. You can cook up your own definition of strain, and it's going to be working just as well as some of these other measures. So let's take a look at some of these other measures. There is something called a green Lagrangian strain. This is going to be an important measure of strain for us when we are looking at these finite deformations of a body. So this is defined as half of L square minus L0 square, or if you simplify that out, you get basically half of lambda square minus 1. Once again, if lambda is 1, this is 0. So it satisfies that condition. An Eulerian-Almansi strain, which is 1 minus 1 over lambda square. This is also something that is extensible to large finite deformations. There is something called a logarithmic strain, where people said that, okay, you know, when I'm talking about change in length, over original length, then depending upon what process I undergo through, let's say I have this bar, if I really push it hard and stretch it twice its length, then during the deformation process, the change in length keeps on growing through the deformation process, right? When I say delta L over L, all I'm doing is taking the final over the initial configuration, but maybe that's not a good measure of strain. So people said that, okay, we'll do change in length over the entire process and integrate that through the deformation process. So something like delta L over the current length integrated basically over the entire deformation process, which gave you 1 over L dl, and that of course happens to be just logarithmic logarithm of lambda, logarithmic of the stretch. What is log of lambda when stretch is 1? 0. Log of 1 is 0, and again it is a monotonic function, so it satisfies the definition of strain again. So, but none of these measures of strain account for the fact that, or have a very fundamental assumption behind them basically. What is the assumption? Right. So the strain is uniform. The strain rate, it would be rate. When we use the word rate, it kind of implies a time-dependent thing. But what we are saying is that the strain is the same everywhere in the bar. That's the underlying assumption that we are using here, which may or may not be true. So normally or usually strain, if you can imagine this bar, clearly it has a hole here. Maybe there are some more holes, and actually the cross section of this bar also is, there are some inscriptions and all that, so that the cross section changes from point to point. If I were to pull it, wherever the cross section is thicker, there would be lesser strain. Where the cross section is thinner, you'll have bigger, more strain. So just trying to capture all of that with a big homogeneous equation that says change in length over original length is not appropriate in most circumstances. So what we need is a more precise definition of strain. Um, this strain, as I was saying here, is just an average measure of strain for the entire bar. It does not capture that local strain is always local. Strain at a point is what we want to talk about. So in order to come up with something like that, you have to visualize what is the deformation of each and every point in the bar. So what I've shown you here is that process of um, how an undeformed bar A0 to B0, due to some external uh, loads or heat or whatever, goes to this new position AB. Each and every point of that body is mapped in a one-to-one mapping from the undeformed to the deformed configuration. Okay. Now, since I've introduced this word map, we are mapping points from the undeformed to the deformed configuration. You can think that this X, which defines the deformed points in this body, can be expressed as some function of the undeformed points. So the undeformed points I am denoting with Z along the Z axis, and the deformed points I am denoting along the X axis. X would be some function of this Z. Um, the simplest function is X equal to Z. What does that mean? X equal to Z? No deformation, right? Which means stretch is equal to 1, and again no strain under those conditions. But in general, if you look at some small infinitesimal body in the undeformed configuration, that could be something like dz, this black bar here. It maps to some deformed body dx, shown down here. And what we are going to do is we are going to try to visualize how this deformation can be expressed in a mathematical way. So one way to do that is to draw the undeformed body on the horizontal axis that I'm calling Z here, and mark the corresponding points of that map on the vertical axis that denotes X here. I can do that since it's a simple one-dimensional body. For two-dimensional body, it's not possible to do this. But it kind of correlates each and every point, that if I have a point somewhere down here, I go up to that point, and I know now that the position of this body is somewhere here. So this blue curve that I'm showing you, that really is the function phi of Z. So this is one way to visualize this map. If I were to try to calculate what is the change in length, or not change in length, but the final length dx over the original length dz, and plot it over the entire length of the bar. So just taking one point by point, where does each point go? If I were to plot that, that would be nothing but the stretch. So stretch at point A0 is plotted up here. It kind of looks very similar to this shape now, but it's kind of oriented as a function of the undeformed variable Z. So stretch, the important thing here is that stretch becomes a field variable, that at different points in the body, you have different amounts of stretch. So what we can do is to express dx as lambda, a function of z, where if you're trying to find out for some small dx on the deformed body, that would be equal to lambda times dz. So this one-dimensional quantity stretch that we have introduced helps us correlate uh, how the change in length of any infinitesimal body in the undeformed configuration goes to the corresponding infinitesimal length in the deformed body. So this way of visualizing this change in lengths is going to be very important as we go forward. And as I said, we are going to visualize lambda z, the stretch, as a function of z, as a field variable. This is just going to be defined as dx over dz, which is consistent with our initial definition that stretch is equal to final length divided by original length. That's what we said all the way up here, right? Stretch is final length over original length. This was an average for the entire bar. But here we are talking about at each point we could have a different stretch. Okay. Now all of this is just for this one-dimensional body. But what we're going to try to do is to extend this ideas for something that is a finite sized body in 2D or in 3D. So in order to do that, we are going to extend this idea of a deformation map in terms of a deformation map or a displacement map. So what we are going to say is that if I have some body in the undeformed configuration, which I'm showing, for example, here in black, we want to find out how or what is the corresponding position of each and every point in that body in the deformed configuration. So to do that, we are going to say that you pick a point z in the undeformed configuration, and you have a map variable which is also a vector that acts that's a function of that undeformed position z, and that is what is going to be defining a map in 2D or 3D. So this thing is what allows us to extend these ideas from 1D to 2D and 3D. Pick a point in the undeformed body. I can define some function phi which will take that particular point to its corresponding point in the deformed configuration. That's all that this map is. Okay. What else do I want to say here? All right. You might be familiar with something that is related to this deformation map. You might be familiar with something like the displacement field. So if I say that x is equal, or actually let me define displacement. You remember what displacement is? What is displacement of a point? Final position minus initial position, right? That's displacement. So if I have a point, some point z in this undeformed body, I know that the initial position is z. So whatever I come up with the final position, I have to subtract z from it. The final position is just given by phi times or phi of z. That's phi of z minus z. That's the displacement map. So u here is the displacement field, or sometimes we can visualize that as a map as well, displacement map. And phi here is called the deformation map. Okay. A very simple example here of what a deformation map might be. But before I go into that, for most problems in mechanics, it is this deformation map phi that is the unknown, right? This is phi is what we want to find out. If I have a structure, I know its boundary conditions, its supports at places, I know its load, and I know its material properties and everything. What I want to find out is the final deformed shape or the final displacements of each and every point, right? So it is this map that we want to find out, that we want to solve for. So in going through all of these next chapters 2 and 3, what we're going to do is to try to set up a problem in such a way that will allow us to find phi. But for now, we are going to assume that we know phi, and we're going to try to visualize what a particular map looks like. So here's what some simple maps look like. If I have a translation, if I take this body that is shown here in black, and let's see if I can capture that. Yep, if I just translate that to this new position, is there any deformation? No, right? But so when we calculate the strains and everything finally in a couple of lectures, the strains will come out to be 0. But how can I define this? How can I define this as a deformation map? Even though there is no deformation, how can we set it up as a deformation map? With coordinates, yes. So give me any point in the original body. Each and every point in the original body is displacing by this amount u, right? It's the same displacement for each and every point. So we can write this simply as x is equal to z plus u, which is equal to, or which is basically the function. So maybe I should have written it in this way. I'll move this to the side a little bit. We are saying that x is defined by a deformation map z, where deformation map phi, where phi is equal to z plus u. So if you give me some point in the initial configuration z1, z2, z3, all I will do is to add the corresponding displacements u1, u2, u3 to the coordinates of that point, and that will give me the coordinates of the corresponding displaced point. No surprise there. That's a very simple translation map. How about uniform expansion? So let's see if I can visualize that. So I'll capture this guy. Originally the body was up here, okay? And if I'm talking about uniform expansion, let's say I take the body and just grow it twice its size, something like this. That's uniform expansion. What we are doing really is, from the original position, pick any point in the original position. If its coordinates are z, the final coordinates are how much? 2z. In this case, if I'm expanding it by 2, then yeah, if initial coordinates were z, the final coordinates are 2z. Or if I'm expanding it by some other amount alpha, then the final coordinates would be alpha times z, right? So indeed, we are looking at the map which would just be alpha times z. That's an example of a uniform expansion. I'm missing underline under phi here. So in components, no surprise there, alpha times z1, z2, z3 gives me the corresponding position of a point from the undeformed to the deformed configuration. So once again, maybe you can verify that what is the new position of a point that is at the origin in the undeformed? The origin, it remains right there, right? Anything on the even axis stays on the even axis, it just moves alpha times its original coordinates. So same thing for E2, E3 axis. That's what basically a uniform expansion would look like. All right. Very quick example of this approximate bending, and then we are done. So let's take a look at this simply supported beam in the black configuration that I've drawn here. It's a 3-dimensional beam with a rectangular cross section. On the right hand side, I have a roller on the entire edge. On the left hand side, I have a pin on the entire edge. I am applying some distributed load over the top surface. Under all of that load, this simply supported beam would kind of bend in this shape, where you can imagine that the rollers would slide to the left. Of course, the middle cross section of the entire length would also slide to the left a little bit and go down. So what I'm suggesting here is that an approximate map. In real life, this map would not be correct, but let's first check whether this map even makes sense. What we are saying is that give me some point Z, Z1, Z2, Z3 in the black configuration. I want to know where that point went into the in the deformed blue configuration. So for example, if you think about this black cross section, something in the middle up here, we are saying that anything that has a z1 coordinate, that is along the E1 axis in the horizontal direction this way, will get contracted by something like z1 over L times delta 1. What is delta 1? That is the shift of the right end. So when we say for the first component that the shift on the right hand side is delta 1 to the left, we are assuming that corresponding points throughout the beam will also shift in a proportional way to delta L, delta 1, okay? What we are saying is the right hand side is shifting by delta 1, so all the points to the left of it will have a proportional shift in the amount of delta 1, where the proportion will be simply equal to z1 over L. So go to any point z1 out here, its shift to the left would be z1 over L times delta 1. x2, that is the displacement in the y direction. We want something that goes to 0 at x equal to 0 and 0 at x equal or z1 equal to L, and in the middle it should have the maximum displacement. So sine, this does look like a negative of sine function, correct? So z2 minus some factor delta 2, which is the vertical drop here, times sine of that number, sine of that same z1 coordinate, and z3 we are assuming remains the same. So this map, I hope you are able to convince yourself that this is a map which approximately depicts bending. Okay, in real life this is not how beams bend. In real life we'll try to find out how beam bending happens. And one of the real life solutions is given in a different book, which actually, okay, I'm way over time here. Which I'll go over much more in detail next time. So let's stop here. We'll meet in this room 5:30 today. By the way, a sooner time than 5:30, would that work better? What anyone's last class on Friday?
This one.
This one, really? There's no, I mean, not for today in general. There's concrete after this, right? There- So what is your last class on Friday? 1:20. Okay, so presumably I could schedule something from 1:30 onwards? Okay, all right, so I'll try to find a room for next week, but today we'll meet at 5:30. All right?
I just had a quick question about the like kind of the normal vectors. So there was a question about a tetrahedron, and you can tell that like it kind of lied in